calculus class. So this is our first topic in Unit 2, and it is about rates of change and tangent lines. We are going to start off with talking about average velocity, which should be a review from your Algebra 1 class. So the average velocity of an object is the distance the object traveled divided by the elapsed time. That is, average velocity equals distance traveled divided by time passed. In particular, if S equals f of t describes the position of a moving object at some time t, then the average velocity of the object between time t and some other time a is given by the following: f of t minus f of a all over t minus a. And hopefully this looks familiar, and I'm hoping that you're thinking in your head that this looks like the slope formula of a line, because that's what it is. So when we're finding average velocity, we're going to use a car example, sort of similar to when you guys did the 20-minute ride car problem. But the difference here is that you're given an actual equation for our distance. So we have a car stopped at a traffic light and begins to move forward along a straight road when the light turns green. The distance s in feet traveled by a car in t seconds is given by s of t equals 2 times t squared, where t is between 0 and 30. So we want to know what is the average rate of change of the car from t equals 5 to t equals 10. Well, we know that average velocity is given by the change in distance over the change in time. So to get the change in distance, we have to find out the actual distance at 10 seconds and at 5 seconds by plugging in 10 and 5 into our 2t squared equation. So by doing that, we eventually will get 30, but don't forget that you do need to include units, so it's actually 30 feet per second. So what does the average velocity represent mathematically? Well, if we look at the red graph represents the distance equation for our car, 2t squared, and this line right here is the line that goes through the point at t equals 5 and t equals 10. And like I mentioned earlier, the average velocity represents the slope of this line. And from geometry, does anyone remember what this type of a line is called? Usually it was when you had a circle, but we're actually going to be talking about in terms of a curve. So we actually call this line a secant line. So, little review of secant lines. A secant line to a curve is a line that goes through 2 points, P and Q, on the curve. We will denote the slope of the secant line through PQ by M sub PQ, so the slope of segment PQ. So if we are given this lovely graph of some function, this graph will tell us that if we have y equals f of x is our function, and p is the point at a comma f of a, and q is the point x comma f of x, then the slope of the secant line is given by, well, change in y over change in x. F of x minus f of a over x minus a. In other words, average velocity is the slope of the secant line. So let's go back to our car example. What if now I want to know how fast the car is going at after exactly 10 seconds? So this is very similar to what I was asking you guys to do in the 20-minute ride to calculate your speed at precisely 10 minutes. So we're going to calculate the velocity of the car at t equals 10. Well, choose a time value close to t equals 10 and calculate the average velocity within that time interval. Keep doing this until you think you can give an approximate value. So let's say I pick the time 9.99. So I plug in the 10 and 9.99 into my function, and after evaluating, I get approximately 39.98 feet per second. Now, of course, if I'm not satisfied with that, I can pick a value even closer to 10 seconds and plug it in. And after simplifying, I get approximately 39.98 feet per second. So I can approximately say that the velocity of the car after 10 seconds is about 40 feet per second. And I know that this was not how you would have done it with your experiment with the 20-minute ride, because you guys didn't actually have a function for your data. Does this process remind you of anything? Picking a value really close to the value that you actually want the velocity at? I'm hoping you set a limit, because that's what we're doing. We were calculating a limit. And what were we taking the limit of in this car problem? Well, we were taking the limit of the average velocities. In other words, the limit of the slopes of the secant lines, since we said earlier that the slope of the secant lines represents average velocity. So this leads into instantaneous velocity. The instantaneous velocity is the limiting value of the average velocities over shorter and shorter time periods. In particular, if S equals f of t describes the position of moving object at time t, then the instantaneous velocity of the object at time a is given by the limit as t approaches a of f of t minus f of a all over t minus a. Notice this right here is our slope of our secant line. To get the instantaneous velocity, we have to take the limit of that. So, what is a tangent line to the graph of a function? Well, a line L is said to be a tangent to a curve at a point P if the line L touches but does not intersect the curve at P. So here are some examples of what tangent lines look like. And you probably remember from geometry, tangent lines from circles. Well, in calculus, we take tangent lines on curves. So notice in this picture, we have a tangent line at this point because it touches the curve specifically at one point. Whereas it's not tangent here because it basically intersects the curve. So what we do is we're going to be calculating the slope of the tangent line. So the slope m of the tangent line at point P is the limit of the slopes of the secant lines PQ as Q approaches P. So as you can see in this picture, if I was going to take line PQ but move Q closer and closer and closer to P until I get Q basically right on top of P, that means I'm calculating the slope of my tangent line. So that's the idea. You're taking, as Q is approaching P, you're going to get the slope of the secant lines. In particular, if y equals f of x is our function, and P is the point a comma f of a, and Q is the point x comma f of x, then the slope of the tangent line is given by the limit as x approaches a of f of x minus f of a all over x minus a. So this right here was also how we calculated instantaneous velocity. This is only one form of the slope of a tangent line. The other form, so if we have the slope of the secant line, if given by this picture, so if we have point P and point Q, where the x value a is at some value, and we have another x value h units away from a. So that gives us, in order to get the slope, we have to take the value of the function at q. So we have f of a plus h minus f of a all over the change in the x values, a plus h minus a. So I can simplify this a little bit to give me that the slope of the secant line is f of a plus h minus f of a all over h. Now, like I have been saying, that in order to get the slope of the tangent line, you need to take the limit of the slope of the secant lines, because we're going to get q is approaching p. So when we do this, as q is approaching p, that means that this x value is getting closer and closer and closer to a, which means that that distance between these two x values is getting smaller and smaller and smaller. So therefore, that's why we say the limit as h is approaching 0. And then we have of our slope of the secant lines. Note that this is the slope of the tangent line is the same thing as instantaneous velocity. So that's a big deal. Slope of the tangent line, same thing as velocity at a specific moment in time. So, an example. So if we have our function, f of x equals x cubed at -1 to -1, we want to know the slope of the tangent line on this function at specifically x equals -1. So what that means is that I am going to go ahead and take x equals -1 and plug it in to the slope of my tangent line where x is, and evaluate what I know. Well, I can figure out what f of -1 plus h is. I can take -1 plus h and plug it in for x. And the same thing here. Take -1 and plug it in for x. So I get the following. This should feel similar to what I asked you guys to do on the graded assignment in Unit 1. So now I'm going to have to simplify. I'm going to have to expand the -1 plus h cubed, and the negatives will cancel here. So using Pascal's triangle, that's how I expanded. And then after some simplifying, I now have this. And I can go ahead and cancel some stuff, so I can see that the 1's cancel. And at the same time, I can factor out an h. And the h's cancel, which is nice. And now when I plug in 0, I get a value out, which is 3. So this is telling me that the slope at x equals -1 of the tangent line on x cubed has a slope of 3. So now, what is the equation of the tangent line at x equals -1? So this should be a review of Algebra 1. So when you find an equation of any line, you need two things. Does anyone remember what the two things you need? You need the slope, which we calculated in Part A, and then you need the point on the line. Well, we have a point on the line because you were given it, -1, -1. So we already know that the slope of the tangent line is 3, and we do have our point, -1, -1. Sometimes you will only be given the x value, and therefore you'll have to find the y value of the point. All you got to do is take the x value, plug it into your function to get your y value. So, since we have a point and a slope, we use point-slope form. How many of you guys have used this one a lot? This one I know you guys don't use a whole lot. You guys are so used to the y equals mx plus b, but I will let you know that if you have a point and a slope, use this one. You can always solve for y if you absolutely want to. So I plug in my slope and my point, and I can stop. I do not have to solve for y. It does not ask me to solve for y. I wrote an equation. I'm done. That's exactly what the AP test would be okay for. They do not have to have it in terms of y unless it's a multiple choice question and all of the choices are y equals. All right, your turn. So go ahead and press pause and see if you can write the equation of the tangent line on the square root of x when x equals 4. Welcome back. Let's see how we did. So take the limit as h goes to 0 of f of 4 plus h minus f of 4 all over h. Plug it into the square root. Do some simplifying. When I plug in 0, I should get 0 over 0, which tells me I need to do some algebra and rationalize the numerator. Multiply through. Simplify, so the 4's cancel, and the h's cancel. So now I am left with the following. Now let's see what happens when I plug in 0 for h. Simplify, and we get 1/4. So now the slope of the tangent line on the square root of x at x equals 4 is 1/4. I already have my point, so now I can write the equation of my tangent line, and I am done. All right, now let's look at a common example. So if we have an arrow is shot upward on the moon with a velocity of 58 meters per second, its height in meters after t seconds is given by h equals 58t minus 0.83 t squared. Find the velocity of the arrow when t equals a. So this time, we want the velocity at a specific time value, but this time value is a. So instead of plugging a number in for x in my limit, I'm going to plug in a. So now my velocity is going to read as the limit as h approaches 0 of f of a plus h minus f of a all over h. This should look a little bit familiar from that graded assignment last unit. All right, so now I'm going to take a plus h, plug it in for t, and then same with a. I get the following. Now I'm going to do some multiplying and distributing and some simplifying. So when I do that, I expanded the a plus h squared, distributed through the 58. I'm going to now do some more distributing and also look for some canceling. And then I'm going to see if there's anything else I can combine together or cancel. We have that the a squares cancel. And I also notice that my remaining terms have h's, so I can factor out an h. Therefore, the h's cancel. And I can say that once I plug in 0 for h, and this term cancels, that the velocity at some time a is equal to 58 minus 1.66 a. This function is the velocity function, and you can use it to find the velocity at any time value. So people who are in physics and AP physics, I believe Mr. Randall probably will give you just your position function and your velocity function. But now, if you only have your position function, you can now find your velocity function by doing this at some t value, and we just chose a. So now, using the fact that we have our velocity function, at what time will the arrow change direction? Well, this means that the velocity is 0, because when you shoot the arrow up, it's going to have to come back down, and it changes direction right when the velocity is 0. So that means I'm going to take my velocity function, set it equal to 0, solve for a. So I get that the velocity will be 0 at 34.9398 seconds. All right. Another example is given when you have just a table. So this example is very similar to your guys' 20-minute ride experiment. So hopefully after this, if you are unable to calculate your actual speed at 10 minutes, you should now be able to after this problem. All right, so we have the number n of locations of a popular coffee house chain is given in the table. Estimate the instantaneous rate of growth in 1998. So here's 1998. That means, since we're talking about a limit, we want to look from the left and from the right. So we must estimate the instantaneous rate by using the average rates on either side of 1998. Well, can't we find the rate of change between 98 and 97? Can't we also find the rate of change between 99 and 98? Yes, we can. So we're going to do the left and the right. So on the left-hand side, we take our change in the number of locations over our change in year. Simplify it, we get 474. Now we do the right. Change in location over change in year. Simplify, we get 249. And I'm sure this is exactly what happened with you in your guys' car problem. You had the values of your speed within a minute of between the 9th and 10th minute and the 11th and 10th minute. And now what do you do to get exactly at the time you want? Take a wild guess. You average them. So we can average the 474 with the 249, divide by 2, because that's how many we have, and we can approximately say in this problem that we have 361.5 locations per year is the rate of growth in 1998 for the coffee chain houses. Now, if you were unable to do the precise at 10 minutes for your car problem, go back and try it now. Or if you didn't do it this way and you got something a little crazy, see if you do it this way, if you have something that's more exactly what you actually recorded your speed to be at 10 minutes. All right, I hope you enjoyed this lesson, and I will see you guys tomorrow. Bye.